Hi everyone, I'm Yu Wang at Beijing University of Posts and Telecommunications. It's a great honor for me to present my paper here. I'm going to share with you our recent work, MalWhiteout, Reducing Label Errors in Android Malware Detection. Android malware continues to grow and poses an increasing threat to users. Accordingly, Android malware detection have attracted massive research efforts in recent years. Most of them are based on machine learning techniques. In such work, both model training and testing rely on a set of apps and their associated labels. Typically, the labels can be either automatically labeled by antivirus services such as VirusTotal or manually flagged by security experts. However, they have limitations. Manual labeling is labor and time intensive. The results returned by VirusTotal are shown to be unreliable. The noisy labels in the dataset have a considerable impact on machine learning-based malware detection research in both model training and testing. We first discussed the uncertainty of malware labeling using VirusTotal. A common challenge of using VirusTotal is that engines often disagree with each other. In this context, researchers usually define a voting threshold to label malware. However, different researchers would choose different thresholds. The threshold is mostly set based on researchers' intuition and experience. There are no standards on how to label apps based on the detection results of various engines. Besides, the detection results of VirusTotal could change over time, making it more difficult to infer the true labels of an app. For this, we carried out a preliminary study. We had collected over 8,000 samples in August 2019, at which time we uploaded them to VirusTotal for rescanning. After 2 years, we uploaded these samples to VirusTotal for rescanning again in August 2021. As such, we obtained 3 snapshots of the scanning results. We can see each time there are some samples have their labels changed. Thus, using VirusTotal for malware labeling is prone to generate error labels. To the best of our knowledge, the only existing work targeting noise reduction in Android malware detection is differential training. It relies on a heuristic to differentiate wrongly labeled samples and correctly labeled samples based on their loss values in 2 deep learning models. However, it requires multiple iterations, thus falls short in efficiency. Beyond Android malware, label noise is a common problem in machine learning datasets. There are a lot of studies address noisy labels in academia using traditional machine learning or deep learning methods. Some work deals with noisy labels by means of noise estimation and data cleaning. There is also work focusing on robust training from noisy labels. In general, our key idea is to borrow existing noise handling methods to deal with the noise problem in machine learning-based Android malware detection. On this basis, we also come up with 2 ideas for improvement. First, our preliminary exploration revealed that while existing methods can be ported to deal with our task, they still present some challenges, such as some methods can generate intolerable number of false positives. Nevertheless, among them, confident learning seems a viable method, as it performed the best during our preliminary exploration. Confident learning is an emerging framework for characterizing and identifying label errors in datasets and learning with noisy labels. For more details, you can refer to our paper. Confident learning works with a machine learning-based malware detection model to estimate noise. In fact, there are quite a lot of malware detection methods. In our preliminary exploration, we chose 2 open source methods, CSBD and Drabbin, to verify the effect of confident learning. In this figure, we give each app a number and ranked noise samples first. So each app is a data point on the x-axis shown in solid colors when identified as noise. We can observe that both models can successfully detect many true noises, see dense vertical lines on the left, but also have some false positives, see sparse vertical lines on the right. And the false positives identified by the two models are usually inconsistent because the blue and green lines rarely overlap on a straight line. This suggests that the samples in which the decisions of the two models diverge are proven to be false positive. In contrast, the sample detected as noisy by more than one model is more inclined to be true noise. Thus, relying on multiple models may be more effective than a single model. Besides, some app-specific features such as app relations sometimes can help decide the app's label. For example, if two apps have the same developer, their labels are likely to be the same, as a malicious developer often publishes more than one malicious app. In view of this, we carried out a simple preliminary investigation. These 18 apps share the same developer, and 3 of them have noisy labels. Among them, 4 apps are identified as noises by the CL-wrapped CSBD model, of which 2 are false positives, and 4 apps are identified as noises by the CL-wrapped driving model, with 1 is false positive. Whereas the developer-based app relation could correctly identify all the noises. This shows that app relation can facilitate noise detection. However, as such relation cannot cover the full range of apps, it might be a good idea to adjust the noise detection results relying on the app relation. Enlightened by the key ideas, we propose a system called MalWhiteout. MalWhiteout is built atop confident learning. It introduces 2 major components. First, ensemble-based noise detection, which adopts ensemble learning to improve the robustness of noise estimation based on confident learning. Second, app relation-based adjustment, which uses an inter-app relation based on developers to adjust noise detection results. In the first component, we use a 2-level architecture involving multiple base learners and a meta-learner. We select driving CSBD and MLScan as base learners and logistic regression as meta-learner. You can refer to our paper for the detailed model selection. First, each base learner works with its own features and classifier in parallel to output predictions through cross-validation. Next, for each sample, its probabilities predicted by different base learners are concatenated into a new feature vector, which is fed into the meta-learner along with its original label. Meanwhile, the meta-learner performs noise detection by being wrapped into confident learning. Finally, it outputs potential mislabeled samples. Then we treat apps with the same developer as belonging to a cluster and determine the true labels of the samples in each cluster by majority voting. In this way, the few apps in the cluster whose labels are inconsistent with the presumed label will be regarded as noise. Based on this decision, the noise detection results obtained in the previous phase will be adjusted. Next, we conduct experiments to evaluate the performance of MalWhiteout. We investigate 4 research questions. We first introduce our dataset. To the best of our knowledge, the most reliable malware dataset is MalGenome. However, it is old and has a limited number of malware samples. To expand the dataset, we use a reliable way that is relying on security reports to collect malware. Usually, the security companies publish reports to reveal their identified malware. These reports are manually analyzed by security experts with detailed code analysis, and they often list indicators of compromise, which could be used to create malware dataset. We make efforts to create an Android malware dataset called MalReader. The detailed information can be found at the website. Both MalReader and MalGenome serve as the ground truth malware dataset in our study. Besides, we collect benign apps from Android Zoo and sanitize the benign dataset using various total surveys. We keep the number of benign apps comparable to the number of malicious apps, resulting in a total of over 11,000 samples. To examine MalWhiteout's capability on detecting label noise, we create some noisy labels in the dataset from two ways. First, we randomly select a certain percentage of the samples as noises whose labels are manually flipped. Second, we label the samples based on various total scan results using a threshold-based method and check the mislabeled ones as noises. We first evaluate MalWhiteout's overall effectiveness. We evaluate on two kinds of label noises, respectively. First, we evaluate on how well MalWhite detects label noises from random flipping at various noise ratios. We can see as the noise ratio varies from 5% to 30%, MalWhiteout achieved a high accuracy and F1. The percentage of noisy labels in the dataset is significantly reduced. To better understand the practical benefits of MalWhiteout in the context of VirusTotal, we also evaluate using the actual mislabels from VirusTotal. Assuming we set the threshold to 2, 5, 10, and 20 respectively, there are 8, 50, over 100, and over 600 mislabels generated. Taking them as noise, MalWhiteout can identify most of them. However, MalWhiteout also generates some false positives that can be introduced as new noises by flipping labels. With the introduction of new noises, MalWhiteout can reduce the noises by more than half. In the design of MalWhiteout, it's unclear how useful the idea of ensemble learning and applications can be. Thus, we study the results of each case in order to understand the effect of each component. These columns present the results of each of the 3 individual methods, which show varying detection abilities. This column shows the detection results using the ensemble learning approach, which shows significant improvement compared to when using a single model. The last column shows the detection results after the noise adjustment using appellation. We can see it helps reduce the number of false positives. Thus, both the design decisions have made a positive contribution. We next verify the impact of training sets of varying quality on malware detection efforts to see how much MalWhiteout can help improve the performance of existing techniques. We make 3 separate training sets of varying quality. First, correctly labeled dataset. Second, noisy labeled dataset. And after MalWhite revises the labels in noisily labeled dataset, we refer to it as the processed dataset. We can see all the 3 approaches yield minimum F1 values on the noisily labeled dataset. When trained with the processed dataset, the models all achieve significant improvements. This demonstrates MalWhiteout's positive contribution to the existing machine learning-based Android malware detection efforts. At last, we compare the performance of differential training and MalWhiteout. Given that differential training uses feature vectors specified by Drabbin, we also add a control experiment using only Drabbin's features for the sake of fairness. We first focus on the effectiveness of noise detection. We can see MalWhiteout achieves much better results than differential training in all cases, even with only Drabbin's features. The difference in effect is particularly noticeable when the noise ratio is relatively low. For mislabels from VirusTotal labeling, MalWhiteout performs remarkably better than DT. For example, when threshold is 2, MalWhiteout performed worst, reducing the noise by half, while differential training produced an intolerable number of false positives. We next take a look at the time cost of the two approaches. MalWhiteout's two phases, ensemble-based noise detection and application-based adjustment, have a stable time cost within 40 minutes. Differential training reduces the label noises in a gradual way in multiple iterations. Thus, the more iterations it requires, the longer time it takes. Overall, MalWhiteout is much more efficient compared to differential training, being 70 to 249 times faster. In conclusion, we propose a noise detection method, MalWhiteout, to reduce label noises in datasets for machine learning-based Android malware detection. We revealed that various total scan results have significant uncertainty for labeling, posing challenges to existing machine learning-based Android malware detection. The performance of malware detectors can be improved after removing noises by MalWhiteout. Thank you for listening.